this video, I'm going to explain Viterbi algorithm. Concept related to convolutional codes. Problem here is consider one problem. The convolutional encoder shown below using trail structure encode the given message sequence. And decode the encoded sequence with the help of Viterbi algorithm. Here the convolutional encoder is M1, M2, two modulo 2 address are used here. Output 1 and output is 2 here. X1 and X2 are two outputs. X is the combined output of this convolutional encoder. This given message sequence is 11 001. This one is the current message bit. These two are M1 and M2 are the previous two successive bits. Decides the state of the encoder. That means capital M is equal to 2. Constraint length of this above. Constraint length of the above convolutional encoder is m plus 1. That means 2 plus 1, that is equal to 3. First section, encode the given message sequence using trail structure. Trail structure constructed with the help of table, transition table. First of all, we have to create transition table. that is called as a state transition table. By using that this table, you have to construct a trail structure and then encode the given message sequence. This is the first step. Trail state transmission table consists of present message bit M, previous states bits M1, M2. This one is the not previous, this one is the present state. Next state. Outputs X1, X2. This is the message. Here, from this diagram, X1 is equal to M exclusive OR with M2. X2 is equal to M exclusive OR with M1 exclusive OR with M2. M exclusive OR with M1 exclusive OR with M2. By using these two expressions, calculate X1 and X2 values. That is the output of the convolutional encoder. Here M is equal to 2. M is equal to, here M is equal to 2 means M1 and M2. Two previous X2 bits decide the state of the convolutional encoder. For M is equal to 2, 4 possibilities are there. 4 possible states 0, 0, 0, 1, 1, 0, 1, 1. Initially, the convolutional encoder is in a 0, 0 state. Here, M1, M2, 0, 0. That means A state. Let it be A. The possible M values are 0 and 1. M is either 0 or 1. Calculate X1 and X2. X1 is equal to, we know that X1 is equal to M exclusive OR with M1. X2 is equal to M exclusive OR with M1 exclusive OR with M2. Here M is 0. M is 0, not M1. Here M2, this one is M2. Here M is 0, M2 is 0, therefore X1 is 0. Here M is 0, M1 is 0, M2 is 0, therefore exclusive OR operation is also 0. Next state means have to perform some shifting operations. Here M value is 0 is shifted to M1, M1 value is 0 is shifted to M2. Therefore, next state is 0, 0, that is A. Here M value is 0, M value is 1, M2 value is 0, 1 plus 0 is 1. M exclusive OR with M1 exclusive OR with M2 means 1 exclusive OR with 0, 0 exclusive OR with 0. 1 exclusive OR with 0 is 1. 1 exclusive OR with 0 is 1. That is 1, 1. Output is 1, 1. Here, perform M value is 1, shifted to M1. M1 value is 0, shifted to M2. That means 1, 0. 1, 0 is equal to B. Let it be B. Here 1, 0 is B. Next. Consider B state. Present state is B state. 1, 0. Possibilities of M are 0 and 1. 1, 0. That is B. Here X1 is equal to M exclusive OR with M2. 0 exclusive OR with 0 is 0. X2 is equal to perform exclusive operation on these 3 bits. 0 exclusive with 1 is 1, 1 exclusive with 0 is 1. Shifting operation, m value is 0, shifted to m1, mn value is 1, shifted to m2. That means 0, 1. Let it be C. Here m value is 1, m2 value is 0, 1 exclusive OR with 0 is 1, 1 exclusive OR with 1 is 0, 0 exclusive OR with is 0. M value is 1, shifted to m1, m1 value is 1, shifted to m2. That means 1, 1. This one is D. Next one, consider C state. Here 0, 1, 0, 1. C state. Possible m values are 0, 1. Here x1 is equal to 0 exclusive OR with 1 is 1. 0 exclusive OR with 0 is 0. 0 exclusive OR with 1 is 1. Perform shifting operation. M value is 0 is shifted to m1. M1 value is 0 is shifted to m2. That means 0, 0. 0, 0 means A state. Here m is 1, m2 is 1. 1 exclusive OR with 1 is equal to x1. That is equal to 0. 1 exclusive OR with 0 is 1. 1 exclusive OR with 1 is 0. That means x2 is 0. Here perform shifting operations. 1 is shifted to 0. 0 is shifted to 1. That means 1, 0. This is the D state. Last one is the convolutional encoder is in a D state. Consider D 1, 1, 1, 1. This one is D. The possible values of M are 0, 1. 0 exclusive with 1 is 1. 0 exclusive with 1. 1 exclusive with 1 is 0, 1, 0. Shifting operations, perform shifting operations. Here 0, M value is 0 shifted to M1. M1 value is 1 is shifted to M2. That is 0, 1. Here 1 value is shifted here. Here 1 value is shifted here. Both are 1s. That is 0. Perform 1 exclusive OR with 1 is 0. 1 exclusive OR with 1 is 0. 0 exclusive OR with 1 is 1. These are the outputs. These are the 4 states. One is A, this one is C, B, and D, because 2 previous successive bits are M1 and M2. That means M is equal to 2. Decides the states of the convolutional encoder. Next step is, here the given message value here is M is equal to 1, 1, 0, 0, 1. By using this diagram, state transition diagram, here you are in present state A, input bit is 0. Next state is A, output bits are 0, 0. You are in state A, input bit is 1. Next state is 1, 0. Output bits are 1, 1. By using these state transitions, I have to construct the trail structure and then encode the given message. Trail is structure. There are 4 states are available here. First of all, I have to write vertically 4 states. A, B, C, D. Here dots are represented here. One, 2, 3, 4, 5, up to 5. The trail structure is to be expanded. 1, 2, last one is, this one is 5. All the dots in a straight line and avoid the confusion. Like that. Okay. Initially, you are in state A. This one is state A. Input bit is 0, represents a solid line. Input bit is 1, represents dashed line. Goes to next state A. Here next state B. Outputs are 0, 0, 1, 1. Outputs are 0, 0, 1, 1. Here you are in state A. Input bit is 0. That means solid line. Output is 0, 0. State A. Another option is input bit is 1. Input bit is 1. Output is 1, 1. See the another option. Here in the second level, this is the J is equal to 0, L is equal to 0 level. This is the L is equal to 0, L is equal to 1, 2, 3, 4, and 5. Here two possibilities are there here. A to A. Here again we use another one. B, you are in state B. Input bit is 0. Input bit is 1. B to C, B to D. B to C, B to D outputs are 0, 1, 0, 1, 1, 0. You are in state A. Here input bit is 0, solid line. Output is 0, 0. Input bit is 1, dashed line here. Output is 1, 1. You are in state B. This one is state B. Input bit is 0 means goes to C, solid line. With output is 0, 1. Input bit is 0. Output is 1, 0. At level 2, the possible states are A, B, C, D. Here at level 1, only A, B are considered. At level L is equal to 0, only starting state is considered. From this, C and D also consider. C to A here by using this flowchart also. Here C to A when input bit is 0. C to B when input bit is 1. Outputs are 1, 1. These are the two outputs, 1, 1 and 0, 0. And consider D also. D to C input bit is 0. D to C input bit is 0. and D to D input bit is 1. That means 1 0 0 1. By using these flow graphs, signal flow graphs, I have to construct the diagram. Here A to A 0 0. Here A to B 1 1. Here B to C. Here B to C 0 1. B to D 1 0. Next C to A. This one is C to A. This one C to A. With output is 1 1. C to B. Its output is 0 0. Next one D to C. Here D to C. With output is 1 0. D to D 0 1. Next one A to A 0 0. Here A to B 1 1. Here B to C. B to C with output is 0 1. B to D 1 0. Next one C to A 1 1. C to A 1 1. C to B 0 0. Here D to C 1 0. D to D. With the help of these signal flow graphs, that means transitions, you have to construct a trail structure. Next one. Here A to A with output is 0 0 and input bit is 0. A to B 1 1. Next B to C. Here B to C with output is 0 1 and B to D 1 0. B to D. Next one C to A 1 1 and C to A 1 1 and C to B 0 0. D to here D to C 1 0 and D to D 0 1. Up to 5 levels are considered because the M value is the length of the message sequence is 1 2 3 4 5. Now consider here M is equal to 1 1 0 0 1. Here m is equal to 1. First one is m is equal to 1. M is equal to 1 means the solid line represents m is equal to 0. Dashed line represents m is equal to 1. From starting state is A. From that A, consider input bit is 1. Therefore, the direction is like that. The output is 1, 1. The output is 1, 1. The next bit is also 1. That means 1 means solid lines, dashed not solid, dashed lines. With output is 1, 0. Next bit is 0. Next bit is 0 means consider solid line. 0 means solid line. With output is 1, 0. With output is 1, 0. Next bit is 0. That means consider solid line. 0 means solid line. With output is 1, 1. Next bit is 1. Next bit is 1 means consider dashed line. Consider dashed line. With output is 1, 1. These are the inside that circle. The bits are output bits. Length is n. N is the number of outputs of the convolutional encoder. Therefore, encoded sequence is encoded sequence. Encoded sequence is 1, 1, 1, 0, 1, 0, 1, 1, 1, 1. This is the output of the convolutional encoder. That given message sequence is encoded with the help of trail structure. First, A part is completed. Encode the given message and decode the sequence with the help of Viterbi algorithm. Viterbi decoding technique. Viterbi decoding technique. Viterbi decoding technique is used to decode the encoded sequence. This is the transmitter. This one is the receiver. The transmitter sent this information 1, 1, 1, 0, 1, 0, 1, 1, 1, 1. The receiver receives that information. This is the message sequence. M is equal to 1, 1, 0, 0, 1. The receiver receives the sequence and again produces 1, 1, 0, 0, 1. Viterbi decoding technique uses Viterbi algorithm and decode the received sequence. First point here is Viterbi decoding technique. Viterbi decoding technique uses Viterbi algorithm. Viterbi algorithm for decode the received sequence. Second point here is in that algorithm, Viterbi algorithm, divide the received information into code words of length of n bits. Divide the given received code word into divide the received code or received information into code words of length is n bits. And write these code words over each time step of tray list structure in sequence. Okay. In this example, the received sequence is 1 1 1 0 1 0 1 1 1 1. Example here by using this received sequence. Received sequence is Rx is equal to 1 1 1 0 1 0 1 1 1 1. Divide the received information into code words of length is n bits, where n is called as the number of outputs of the convolutional encoder. Number of outputs of the convolutional encoder. In the given convolutional encoder, two outputs are there. Two outputs x1 and x2. Therefore, n is equal to 2. N is small n is equal to 2. Small n is equal to 2. Therefore, the received sequence is divided into the received information is divided into code words of length is equal to 2 bits, because n is equal to 2, number of outputs of the convolutional encoder. That is 1 1 1 0 1 0 1 1 1 0 1 0 1 1 1 1 1 1 1 1. After division, these code words divide the received information is code words of length is n bits, and where n is called as the number of outputs of the convolutional encoder, and write these code words over each time step of the style structure in sequence. See the different time steps are there here. Place these code words 1 1 1 0 1 0 1 1 and 1 1. These are the time steps. These are the time steps. 1, 2, 3, 4, 5 time steps are there. These 5 code words are placed on these 5 steps. Next important point here is second point here is find the Hamming distance between the code word of length n bits of the received sequence and the outputs of the encoder observed on the branches of the style structure. Okay, next consider this one is A state. A to A, we know that A to A here 0 0, input bit is 0, input bit is 1, A to B with output is 1 1. These are the outputs of the encoder observed at these two branches of the style structure. Consider this is the time step 1. In the time step 1, here 1 1 is placed on this time step 1. This one is 1 1 1 1. Find out the Hamming distance between 1 1 and 0 0. First and 1 1 and 1 1. These find out the Hamming distance between these two. Hamming distance between these two is 1 is changed to 0, 1 is changed to 0. Hamming distance is 2. Here 1 is does not change. Here 1 is same as 1 1. Therefore Hamming distance is 0. Here indicate this value in the inside circle and place on the branches of this style structure. This is called as initial Hamming distance is called as branch metric. This is called as branch metric. Branch metric means is the Hamming distance between encoded signal on the branches of the style structure and the corresponding received signal placed on the respective time step. Okay. This is these two 0, 0 and 1, 1 are the encoded sequences placed on the branches of this tile structure. This is the received code word of length is n bits. That means 1, 1. Find out the Hamming distance between 1, 1 and 0, 0 and 1, 1 and 1, 1. These Hamming distances are indicated inside the circle and placed on the branches of this tile structure. Next, third one is path metric. Path metric is nothing but the cumulative action of the branch matrix. Branch metric. Write the path metric by adding the Hamming distance between the received code sequence and encoded sequence on the branches. And then these values are cumulative. Cumulative means again add next time step path metric value and the next time step path metric values. Like that we will get the next time step branch metric value to the previous branch metric value. Example is here initial state is A, here A to A 0, 0, here A to B 1, 1, here A to A to B, here in the first time step the value is 1, 1. In the second time step the value is 1, 0. Here path metric is in the first time step is path metric is 1, 1. Hamming distance between 1, 1 and 0, 0 is 2. Here 1, 1 and 1, 1 is 0. That means cumulative action of the branch metric means consider a second time step. The received code word of length n bits means 2 bits 1, 0. Here 0, 0. Here 1, 1. The Hamming distance between 1, 0 and 0, 0 is 1, 0 and 0, 0 is 1 change is there. 1 plus 2, that means here 3. Here 1, 0 and 1, 1. 1 change is there. Previous branch metric value is 2. Present branch metric value is 1. Add this present branch metric value with the previous branch metric value. 2 plus 1, that is equal to 3. In this way, we have to calculate all branch metrics. Here, from this point to this point, from this point to this point, the path metric value is 3, and this point to this point, the path matrix value is 3. Like that. In this way, I have to calculate path metric values. Next, fourth one important fifth point here is fourth important point here is discard the paths with discard the path with higher path metric value. Higher path metric value. Next one. Repeat step 2. Step 2 means find out the Hamming distance. Repeat the step 2 and step 3 for the paths, for the path with the lower path metric. That means survived path. That means survived path. Survived path till last time step. Last time step. These 2 points are explained clearly in that procedure. Okay, these are the 5 important points related to related to Viterbi algorithm. Viterbi decoder uses the Viterbi algorithm encode the given received sequence. Consider in this example, the received sequence is 1 1 1 0 1 1. One more important point here is Viterbi decoder uses the trail structure. Viterbi decoder utilizes the trail structure for decode the given received sequence. These are the 6 important points. Yeah, okay. The received sequence here is received sequence is represented by capital Y is equal to 1 1 1 0 1 0 1 1 1 1. Tail structure having some 4 states. This one is A, B, C, and D. The received sequence is divided into code words of length is equal to n bits, means where n is called as number of outputs of the convolutional encoder. Therefore, 1 1 1 0 1 0 1 1 1 1. Here 1 1 1 0 1 0 1 1 1 1. These are the time steps. Okay, these are the time steps. Next, next important point here is initial state is A. By using A to A, by using signal flow graphs, I have to construct A to A with output is 0, 0. Input bit is 0. Here input bit is 1. Here input bit is 1. With output is 1, 1. By using this one green color. Divide this into time steps into different. These are the time steps. Okay. Find out the Hamming distance between 1, 1 and 0, 0. 1 is changes to 0, 1 is changes to 0. Therefore, two changes are there. Hamming distance is 2, indicated this here. Here 2, here 1, 1 and 1, 1. There is no change. That means Hamming distance is 0, indicated here 0. Next, A to A, 0, 0. And A to B is 1, 1. This is the initial, this is the path matrix is 2, here path matrix from A to A. Path matrix is 2, from A to B, the path matrix is 0. Path matrix is 0. Next coming to B to C. B to C. Input bit is 1, B to C. B to C. Here value is 0, 1. And B to D. B to D. 1, 0, 1, 0. They can find out the Hamming distance between 1, 0, 0, 0. Here 1, 0, 0, 0 is one change is there. Hamming distance is 1. Previous path matrix is 2. 2 plus 1 is equal to 2 plus 1 is equal to 3. Here 3 is indicated here. Here 1, 0, 1, 1. One change is there. 2 plus 1 is equal to 3 here. 3 is indicated here. Here 1, 0, 0, 1. 1, 0, 0, 1. 1 is changed to 0, 0 is changes to 1. Therefore, two changes. Previous path matrix is 0, 0 plus 2 is 2 indicated here. Here 1, 0, here 1, 0. 1, 0 and 1, 0. There is no change. Hamming distance is 0. In this time step, Hamming distance is 0 plus 0 here is 0. Next one. Here A to A 0 0, A to B 1 1, and B to C. Here B to C 0 1, B to C 0 1, and B to D, and B to D 1 0. Here C to A, C to A, here C to A 1 1, and C to B is 0 0. C to B is 0 0. Next, D to C. Here D to C is 1 0. D to D is 0 1. Here one more important point here is discard the path with higher path metric. Discard the path with higher path metric value. This is the path from A to B is from A to A, here 3. This one is discarded. These two are discarded here. This path is also discarded from this one to, because 3 value here. These two are discarded. Consider these two, 2 and 0. 2 and 0 here. This 2 and 0 means C to A with output is 1 1. C to B with output is 0 0. These two are considered. Okay. Here 1 0. Here 1 0 1 1. 1 0 1 1. The path Hamming distance is 1. 1 plus 2 here is 1 plus 2 here is 3. C to A here is 1 1. 1 1 and 1 0. 1 1 here 1 0. 1 change is there. 2 plus 1 here, that is 3. Here 3 is indicated. Here C to B with output is 0 0. C to B with output is 0 0. Again here 3. Next, D to C 1 0 here 1 0. 0 the Hamming distance is 0. 0 plus 0 is 0. Here 1 0 0 1. 2 changes are there. 0 plus 2 is 2. Again, here draw this one. 0 0. Zero 1. B to C. B to C is 0 1. 0 1, and B to D is B to here. B to D is 1 0. C to A. C to A Fourth output is 1 1, and the C to B zero zero, D to C, here D to C 1 0, D to D 0 1. Here this one, this path matrix, this one and cancel. This one and this one and this one and cancel, because higher values only consider 0 and 2. Here consider this 1 1 and 1 1 0. Here 1 1 and 0 0, because C2A 1 1 and C2B 0 0. Coming to this one, here D to D 0 1, D to D is 0 1, and D to C is 1 0. Consider these 4. Find out the Hamming distance. This is the 1 1. 1 1 is the received sequence of length is 1 and 2 bits. That means 1 1. 1 1 is compared with 1 1. Hamming distance is 0. 0 plus 0 is 0. Here indicated 0. Next 1 1 is 0 0. 2 changes are there. 0 plus 2. 0 plus here 2 is indicated here. 2 is indicated here. Next coming to D. Here 1 0 1 1. 1 0 1 1 means 1 change is there. That is 3. Here 0 1 1 1. 1 change is there. 2 plus 1, that means 3. These are the this 2, this 3, this 3 are cancelled. This one is considered A to A 0 0, A to B. A to B is 1 1. Okay, need not expand this because higher values. Okay, 3 is cancelled. Suppose 2 is not discarded. Here B to C with value is B to C value is 0 1, and B to D with value is 1 0. Here output is 1 1 1 1 1 1 0 0. Different 2 changes are there. 0 plus 2, that means 2. 1 1 1 1 doesn't change. 0 0 plus 0 is 0. Here 1 change is there. This one is 1. Here 1 change is there. 1 plus 2, that means 3. Here 1 1 1 0 1 change is there. 1 plus 2 is 3. This one is 3. These two are discarded. Finally 0 is there. This one is also discarded. This is the procedure. No. Now we have to find out the survival path. That means with the minimum value. Consider this 0. Here dashed lines represents input bit is 1. That means 1. Here from this 0, another 0 is there. Here 2 0 is there. 0. Here dashed lines indicates 1. Here 0 is there. from this point here 0 and 2, the minimum value is 0. Follow this path. Solid line indicates 0. From this 0 and 2 is there. I have to follow this path. Follow this path. Solid line, that means 0. Here 0 and 2, therefore follows this path. Dashed line means 1. Therefore, the given received sequence, the decoded sequence is 1, 1, 0, 0, 1. Therefore, 1, 1. Decoded sequence is 1, 1, 0, 0, 1. This is the same as the given message sequence. This is the same as the given message sequence. Both are same.